To introduce our keynote speaker, please welcome Kyle Griffin, Vice President and General Manager for Commercial Civil Space with Lockheed Martin Space. Kyle.
Thanks, everyone. It's certainly honored and a great pleasure to be here. These symposiums always have such intriguing questions as we look at that. And as I looked at that mission video, you know, one of the things that really stand out for us over the last year and a half is the OSIRIS-REx spacecraft. And we brought back that sample, and I still today look at the pictures and the science that's being gathered from those samples. It's just an incredible, it's been an incredible journey, and I'm sure there'll be a lot more discovery. It's great to be here. Again, I have the honor to introduce our symposium's first keynote speaker, Dr. Nikki Fox, Associate Administrator for NASA's Science Mission Directorate. Dr. Fox has dedicated her career to scientific exploration and has a deep ties to NASA and Goddard Space Flight Center family. Dr. Fox conducted her postdoctoral work at Goddard before moving to the Johns Hopkins University Applied Physics Lab, where she went on to become the chief scientist for heliophysics. Following her tenure at APL, Dr. Fox joined NASA in 2018 as the director of SMD's heliophysics division. Per her official NASA bio, whose words I cannot improve upon, today Dr. Fox oversees a portfolio of nearly 100 missions that explore the secrets of the universe. Now, if I could put that on my business card, I would, but that is the coolest description of her job that I think there is. Dr. Fox is in the right place because she's rewriting the textbooks, is what NASA Science Mission Director does best. Dr. Fox and her colleagues are moving space science forward. Lockheed Martin is proud to have contributed to the trailblazing missions like Hubble, Webb, Juno, OSIRIS-REx, and many others over the decades. We look forward to continuing that partnership with missions like Da Vinci and Veritas to study Venus, and the MUSE mission to better understand the forces in the sun's corona that are driving space weather. I think during this year, heliophysics is going to have a big year, and I'm personally excited for the and looking forward to NOAA's GOES-U weather satellite this spring. GOES-U will host a solar ultraviolet imager, and for the first time ever, a compact coronagraph that will be a new tool for monitoring space weather. And so we look forward to that, and I'm sure it'll bring you back to some of your heliophysics days. We are fortunate to have a public servant and a communicator like Dr. Fox at the helm of SMD to get the public excited about NASA's missions and science. Please join me in welcoming Dr. Nikki Fox.
Wow, that light is bright. Okay, there's a clicker. They told me there's a clicker, and I should be able to use it because I have a PhD, so I should be able to use a clicker. So good afternoon. I am painfully aware that I am standing between you and alcohol. So I will try and make this brief and exciting and interesting. So thank you very much for inviting me to be here. I want to just sort of boil this talk down to three main themes. So after these three main themes, you can take a nap if you want. But the first one is NASA science is delivering no matter what challenges we face. The second is, folks like you are helping us, and we need you to help us to be able to empower and educate our communities and people that stand on hills, and also to actually foster an inclusive environment to really nurture our next generation, because that is what we really need to do. And we do that, of course, by telling our NASA stories and really inspiring the community, inspiring the general public with everything that we do, which is so amazing at NASA Science. So I'll start with, I think I will start, maybe I've got that the wrong way around. Yeah, so down button, but Mackenzie, I had to be holding it the right way around. I was pressing the down button. So as Kyle said, this is my baby picture. So this is the science fleet. And I actually remember standing at the Goddard Symposium this time last year, and it was actually the first talk I gave as the Science AA, and turning around and seeing this on the giant screen and literally thinking, they're all mine. So there are about 144 missions on that chart, covering everything, all different scales of missions, from CubeSats, balloons, sounding rockets, ISS payloads, all the way up to the James Webb Telescope. So literally covering all types of diverse methods of getting our science to space, and also covering everything from the center of the sun to the very edge of our solar system to the very edge of our universe. So it's a beautifully diverse portfolio. The science that we do, I love to think about the interconnections between the science, the really interesting science. Everybody knows this, all the really interesting stuff. It's not even just science. Interesting stuff happens on boundaries. Nothing exciting happens right in the middle. It always happens on the boundaries. And so I love to look at the way that our science is sort of interconnected in SMD. And of course, I could arrange these bubbles in any different order and find nice intersections. And being as I'm a heliophysicist, I could put heliophysics in the middle and connect it to all of them. But it just really shows how interconnected we are. And so I want to kind of take you on a bit of a journey around things that we do in SMD. So I'm going to sort of take you on a journey. And of course, unashamedly, Parker Solar Probe is close to my heart. I love all my children equally, but Parker Solar Probe is close to my heart. So I like to start with Parker. After all, Parker is studying that it is the closest object that we've ever had to our sun. And so it really is, it starts sort of in the heart. Parker Solar Probe, of course, answering questions about sort of the age-old questions, more than 60 years, but really, getting to the crux of what powers our solar wind. How does it impact with all the planets in our solar system? And then, also thinking, how would other stellar winds from other stars interact with planets that maybe could be harboring life? And so a nice shot there of a terrifying moment when we just lifted that spacecraft, $1.5 billion spacecraft, on a couple of pieces of wire out of the huge vacuum chamber at NASA's Goddard Space Flight Center, getting it ready to go off to Kennedy. So, understanding our sun is so key to everything that we do. Not least because we love to celebrate our sun. As Kyle mentioned, the sun is having a very, very big and glamorous year right now. It is the heliophysics big year. We kicked it off in October of last year with that beautiful annular solar eclipse, an extremely unusual and fairly rare eclipse event. It will cover the eclipse that was coming up in April. And I hope that you have all made your travel plans already to go and see. Ooh, okay, I think this may have died. Oh, no, there it is. Did we get a solar eclipse? Never mind. We're supposed to have a solar eclipse map. So you could, I've got operator error, but I hope you found your location, and I hope you made your hotel reservations already, because there are none. So unless you are, I actually have friends who are taking tents now because there's nowhere to stay, no rental cars and nowhere to stay. But despite that, if you are not able to go and experience totality, fear not, NASA Science will bring totality to you. So you can join us with our friends at Office of Communications, and of course all our partners. Huge thanks to NSF, to NOAA, to USGS, to all our partners who are joining us for the Eclipse event. So it promises to be absolutely amazing. Also, the other thing that's making this year so incredible is we are in the real run-up to solar maximum. It is predicted to be sort of mid-2025. Man, our sun is busy right now. And our wonderful Solar Dynamics Observatory continuing to take amazing images of all the big flares that are happening, that are actually coming and impacting us. We're already seeing those space weather events. And I just caught the tail end of the panel here talking about all of the impacts. We have to worry about it because it affects power grids, undersea cables, pipelines, spacecraft in orbit, and of course, our astronauts. So as I continue, I hope to go around this wheel. There we go. Okay, so talking about protecting our astronauts, it's really hard. I can't actually see that one, so I have to keep doing that. I'm sorry. You know, we actually, one of the reasons we need to study our sun is because we send our astronauts up into space, and they are definitely susceptible to the vagaries of our star. And we love to be able to do our science in microgravity. There's so much great science that we have been doing on the International Space Station for 20 years. We really, you know, we just have our new decadal for the Biological and Physical Sciences division, and really focusing on living and adapting to life in space. So we have a lot of experiments that we do. Come on. One more. There we go. A lot of experiments that we do on the space station. You're seeing our astronauts there. One of the new programs that will be kicking off is a rapid. It's called Cirrus, and it is basically training astronaut scientists to do science in situ. So instead of taking decades to do some of these experiments where you design your experiment, launch it, do the science, wait for it to come back down, get your results. We're actually now starting to do the science in space, changing the conditions, being able to look at how the human body is adapting in space, and also looking at all kinds of organisms, from like pepper plants to fruit flies to the human body, as we prepare to adapt and live in space, live and work in space, as we sort of think about that sustainable lunar presence, and then of course onto Mars. So with the is that Artemis? Yes. So with Artemis, not only are we doing science now in Leo, but we're also now taking advantage of doing science in Artemis. And with Artemis 1, it was that we were able to actually go and do science sort of out in deep space. And so that was the first time that we were able to really look at the effect of microgravity and deep space radiation on several different species like algae, fungi, seeds, and yeast. So things that a lot of them actually that kind of have the same gene expressions as some of our own organisms do. Looking at how different sort of conditions from them either made them more susceptible to being hardy to be able to stay in space, or maybe less susceptible, and what kind of things would adapt for us. Through the Artemis program, so there's obviously a beautiful picture of the Artemis launch from last year, but the Artemis program really ushering in our Moon to Mars strategy. And so doing the science that we want to do on the Moon, and then of course leaning forward to the science that we want to do on Mars. And getting to things that we do on the Moon. We actually will be putting together all of the assets that we currently have. So we have the orbiting spacecraft, like the Lunar Reconnaissance Orbiter, together with everything that we have on the surface, which I'll get to my big proud moment in a moment. But really, again, taking advantage of all of these missions together. This is a beautiful image from Lunar Reconnaissance Orbiter, and we rely on this. It's been going for such a long time. We rely on it for giving us really accurate and really high resolution images of our moon. And of course, we also rely on it to find our landers. So when we land on the moon, LRO is always the one that we go and we rely on to get that sort of pinpoint accuracy of where our landers are. So relying on the science that we're doing here, allowing us to do great science for Moon to Mars. Again, a sort of integrated strategy that we have of pulling together many different disciplines. And so we're already getting ready to send astronauts to the moon by studying the effects of microgravity and radiation on the human body, also getting ready to provide space weather for our astronauts on the moon. The Lunar Gateway will actually house the Hermes payload, which is going to be, it's actually the first space weather payload to be on a human-rated vehicle. And that will be providing that critical information about what is going on in the cislunar orbit to protect our astronauts. Of course, all of the lunar science that we're preparing to do, and then leaning forward to Mars, as we obviously, we already have our rovers down on Mars, doing the first part of that Mars sample return, taking these samples, putting them in the titanium tubes, just waiting for us to figure out how we're going to go get them. But we're really excited about that. And then later this year, we'll launch ESCAPADE, which is the heliophysics mission to Mars, really studying the solar wind around Mars and providing those sort of initial measurements that we'll use to provide a space weather forecast eventually for our astronauts down on Mars. One other mission that we're excited about is Viper, and Viper is going to be carrying 3 science instruments, and it will use a drill about 1 meter long to actually look at sort of what is in the soil in the lunar regolith, looking for water, obviously with looking for volatiles, but looking at different locations and different depths beneath the surface. It will also go into permanently shadowed crater regions, and again, look for things that we might be able to use for a sustained presence on the moon. It also extends our CLIPS program, and I'm sure you're familiar with, that's a nice picture of one of the tests of Viper. Viper will be, as I say, this is in a sandbox, trying to figure out how to actually roll in this very, very sticky regolith, and also how to deal with incredibly long shadows. It's going to go down to the south pole of the moon, and you really don't appreciate what shadows look like. Little, fairly small craters, when lit from a certain angle, make enormous shadows. So it makes driving that rover very challenging. But as I say, it continues with our CLIPS landers, which we're very excited about. This is our partnership with commercial providers, and we've already had 2 launches. The first one, Astrobotic, the Peregrine lander, we still think of it as a huge success because, number one, that is a company that's never built a lander before, built a lander and delivered it. Yes, there was an issue shortly after the launch, but hats off to an incredible team for very open, transparent communication and getting every single bit of science that they could from the instruments that were on that lander. But of course, just last month, we soft landed on the moon with Intuitive Machines. Congratulations to them. It was an extremely exciting and tense event as we waited for news that we had touched down. That was a beautiful partnership, again, with technology demonstrations. So not only do we have science instruments on these landers, but we have a lot of tech demos together with commercial payloads. And when there was an issue with their sort of precision landing system, we were able to quickly, with the help of our friends at Langley and Marshall, to actually pivot to use the LiDAR that was on there as a tech demo as the sort of landing system. So we were really, really proud to be part of that, and great to be back on the lunar surface after 50 years. Okay, so why do we study the moon? Why do we want to know about what it's made of? We want to know about the sort of makeup and the composition of a lot of our planetary bodies, largely because, they hear talking about OSIRIS-REx, which of course I'm going to highlight OSIRIS-REx because it was a highlight of last year for me. But we want to actually look at, is it possible that asteroids crashed into the planet when we were first forming and brought water? How does life start? What are these asteroids made of? Really excited with this beautiful, beautiful image of our capsule that soft landed. I made a joke, it looked like somebody was putting a cup of tea down on the table. It just soft landed. And thank you very much to Lockheed Martin for getting really close to the road as well. That was above and beyond. And we've already got great results from the sample, of course, bringing back more than twice the requirement at 121.6 grams of the asteroid Bennu, already having found water and carbon in those samples. I actually got to go out to Johnson for the Intuitive Machines landing, but last month, and was able to see the samples from Bennu, and also the really creative, what looked like sort of an old-fashioned can opener that they had to use to get those final bits of hardware out to actually open the sample. But really great to see that. Also highlighting the importance of bringing samples back to Earth, because we will distribute for everybody all over the world 25 to 30% of that sample, and the rest of it will be kept for future generations, just as we've done with the Apollo samples. And if you are lucky enough to be able to go and see the Astromaterials Lab out at Johnson, you'll see the size of the mass spectrometers and things that they have to now analyze those lunar samples that were not available 50 years ago. So it makes it just so important that we keep some of these samples for our future generations. But of course, the thing that we were excited about was finding signatures of water as well as carbon in the asteroid sample. And it just goes along with what we do. We follow the water. We want to look for planets or planetary bodies that may have at some time sustained life, or maybe have the building blocks of something that will allow us that would have allowed life to be sustained. So Europa Clipper, launching in October, very excited about that, and looking again for whether or not we actually could have life sustained on Europa. And then leading into Dragonfly, which is a very exciting mission I'm super excited about, which is going to hop around the largest moon of Saturn, Titan. Titan is particularly interesting to us because it apart from just having the possibly the building blocks of life, it's the only moon in the solar system that has a dense atmosphere. It also has like a hydrology cycle very similar to Earth with methane, and we think some very complex organics as well. It is not a life detection mission. What we're looking for is really what were conditions like right before life started here on Earth. We're very noisy. Life is very noisy here. So it's very hard to figure out what the planet was like before life started. But by going to destinations like Titan, we hope to be able to get more information about that. One of the big things, of course, we do, as Kyle said, is study the secrets of the universe and look continually for planets that might sustain life. So with the James Webb Telescope, that's something that's really built on the legacy of the sort of first exoplanet observations from Hubble, and then with TESS and Kepler. But of course, Hubble, JWST doing much more than just look for exoplanets. This is a recent image of a spiral barred galaxy, NGC 1512, if you're into that kind of thing. This is a really stunning image, and you're looking with the infrared at the sort of the bright, shining dust clouds, and the sort of really amazing jagged edges and the real sort of depth that you're looking at that. But this is not the first time we've imaged this particular galaxy. And if I add that, you will see a beautiful Hubble image of the same galaxy. And this to me really shows the power of why we need multiple ways of looking at our universe or even our home planet. Because when you look at that with Hubble, you see a very different view. And you're looking invisible and ultraviolet. The dust actually absorbs the visible and the ultraviolet light, but then it re-emits it in infrared. And so the areas that look sort of dark and empty, you can see are very, very bright and vivid in the James Webb Telescope. I just love this image. I got to be honest, I love this image. But if we also build on some of our older missions, and getting to Chandra, if I can do that one, yes. That's another great example of how we put our different types of data and sort of layer it together. So I think this should give me, yes. So a little while ago, the James Webb Telescope imaged this extremely, extremely distant galaxy. And because it looks very interesting, it's an extremely old galaxy. It's one of the earliest galaxies that we've imaged. Chandra then turned and imaged the same location now in X-rays, and was able to actually see this really image the oldest black hole that we have actually identified. We couldn't do that with even the James Webb Telescope, but by putting these two together, Chandra, of course, needs to know where to point. And so by doing this incredible imaging with James Webb Telescope and then having the power of Chandra being able to turn and look at it, we were able to do this incredible, incredible science. So now imaging a massive, massive black hole, but also we think the oldest black hole we've detected to date. So yay missions. And then leaning forward to the Nancy Grace Roman telescope, which actually is basically a survey. It's the first big survey astrophysics mission, and they are going to actually image like 1 billion galaxies. So, you know, not much, just 1 billion galaxies in their prime mission. And if you haven't had a chance, I'm sure Mackenzie would love to show off the Roman mission in the clean room at Goddard. It is really worth seeing. It is a stunning piece. Really excited about this, doing really well, on budget, on schedule, yay Roman. Also, Roman will carry with it a coronagraph, so with a tech demo of a precision instrument to block out the star, the light from distant stars, to help us actually look for exoplanets and planets that could harbor life while we're doing that. Also allowing us to look at the dark energy and basically the dark universe. So again, all these missions working together. And then my current favorite thing, Habitable Worlds Observatory, which is going to be the next big NASA flagship mission in astrophysics. Really, again, building on the heritage of everything that we have done to date. So as per the decadal, it will have a telescope the size of Webb, it will have the wavelengths of Hubble, and it will have a coronagraph, which is like the next generation of the one on the Roman telescope. So really building. So not only do we build and layer the science on top of one another, but we build and layer on the technology advancements of each of our missions. So we are kicking off the Habitable Worlds Technology Program. We'll be setting up a project office at Goddard and kicking off all the work to do all the technology maturation necessary to then move forward with this next mission. It's kind of dubbed the Habitable Worlds Observatory right now. I really hope we keep that name, by the way, because I think it's really cool. So this is kind of an example with astrophysics of how we layer data. Of course, I could have picked any one of our disciplines, and absolutely we could. This is so key to what we do in earth science. So we recently, it's just been, I think they've just celebrated an operational year with the SWOT mission that kind of brought oceanographers and hydrologists together to do the first really in-depth study of the Earth's surface water, looking at just how the ocean kind of surface is changing, and also looking at all of our inland water. I mean, looking with precision down to lakes about the size of a couple of city blocks. We can image almost every large river in the world with this amazing mission. It's using radar technology to look at the changes in our water, again, either on land or, inland water or our coastal regions, and finding these differences, finding where we have a lot more water than we thought and often a lot less water. So maybe helping us understand why some regions are experiencing terrible flooding while others are experiencing terrible droughts. Another mission that launched very recently, which I'm very excited about, is PACE. Yay, PACE. So PACE, a brilliant synergy. So SWOT looking at the surface water, PACE looking at the health of the basically beneath, looking at the health of our oceans and also our atmosphere, looking at the aerosols in our clouds, but really focusing on ocean color. So telling us about like the the marine superfood, phytoplankton, the kind of base of every single food chain that we can think of, looking at the health of it, looking at whether or not it's a harmful phytoplankton, whether or not it's a healthy one, will have big impact on our economy, on our fisheries. It's just the mission that keeps on giving. And I'm very sad that the next image I have, and I'm looking for an earth science person to glare at, is just a launch, because I am waiting for those first light data, guys, okay? And I will tell you that I saw them. I had a sneak peek and I was looking at the PACE data. Mackenzie's nodding because she saw it at the same time. And I'm literally sitting in my office going, oh my God. And somebody thought I was having some sort of event. But I was just looking at the PACE data. And I tell you, if you think your planet is beautiful, wait until you see it through the eyes of PACE. And I've only seen one orbit so far. So I cannot wait, and I know it's next month, I think, that we're doing the big reveal, but I can't wait to come back and show you all the images from PACE, because it'll be the entire presentation. It is so exciting. And then, another piece of the earth science puzzle is really looking at the air that we breathe. Now, PACE also, by looking at what's in the clouds and what's in our ecosystem, also telling us about the air that we breathe. But we also launched Tempo last year as well. That is in a hosted payload in geosynchronous orbit, looking down at the US, basically the entire US. So from the Pacific to the Atlantic, from the Gulf of Mexico to the oil flats in Canada, and providing hourly, very, very high resolution maps of pollution in the air that we're breathing. So looking at ozone, looking at, the stuff that we really don't want to be breathing, actually, with unprecedented accuracy. And so obviously we have a number of missions that give us this data, but with Tempo, we're continually staring down at the US. And so we are able to do things like analyze rush hour and look at how the air changes during rush hour. We can also provide pollution maps, literally down to neighborhoods. And so as always, we're working with our partners to make sure that we get that data into the hands of people that really need it. And one of the ways that we do that is through our Earth Information Center, which is a beautiful installation that we have at NASA headquarters. And if you have time while you're in the DC area, please come down and see it, because it really is amazing. It allows you to sort of experience what it might be like to float in an atmospheric river. And if anyone doesn't believe in atmospheric rivers, they should have visited JPL 3 weeks ago, because man, it was raining. But you can see here how we're sort of interacting with the public, just really showing them how NASA data, particularly earth science data, impacts them. We have testimonials from farmers who basically say, I don't start working in my fields until I've pulled out the app and looked at, what the water is going to be like, the water level is going to be like today. If you can't get down, I understand it's very busy. If you can't get down to NASA headquarters and see it in person, earth.gov is our beta tested version of the sort of virtual component. And we're doing this, as always, with our incredible partners, with NOAA, with the EPA, with FEMA, with USGS, and just, all of the people that really have a stake and really care about our planet, frankly, and how we are going to protect ourselves. So in the last 20 minutes or so, maybe a bit more, I have taken you on a tour of about 20 NASA missions, and how they're all connected and how the science that we do really is connected. I could, trust me, stand here for a lot longer and talk about all 144, but you don't want me to do that because there's alcohol outside. But I really wanted to use this as just a way to get across the idea that when you're out and you're educating people about NASA science, it doesn't matter which your own mission is, it connects to the whole of NASA science. And so we really want you telling your stories about NASA science as a whole. And it's extremely important. And not only, do we have all these amazing missions and we can talk about them forever and, how wonderful they are, but really space does more than that. Space literally creates awe and it creates inspiration. When you look at the planet in different ways, and this is one of my favorite images, and it's also incidentally the book that Mackenzie did her swearing in, The Pale Blue Dot. We have a joint love of this particular book and image. But that's one of those where you look at it and you think, my God, the planet is so tiny. And yet every single thing that we know, every person, everything that has ever lived in history has lived on that little dot. And so we need as a community to take care of our planet, but also to take care of the space around it, and particularly to really further what we do. Use these kind of stories, use these kind of images to inspire the next generation, and to tell our stories wide and tell them loud. NASA Science delivers every second of every day of every year. No matter what challenge, we will do great things together. And I really appreciate your time today. Thank you.
Take time for a couple questions. Does anybody have a couple of quick questions? Quick questions. We've mentioned alcohol a couple times already.
Yeah.
So. I'm not seeing it. Are you going to stick around?
Yeah.
Okay.
There's
She'll
alcohol.
be out at the reception. So if you do, please step up and ask her.
Yes.
So thank you so much. Appreciate it. So wait, before you go. So a couple of quick things. So thank you very much for being here today. Thank you very much to our hosts here at University of Maryland and the entire team at Goddard for helping put this together. Next slide. Thanks to everybody for that. Thank you very much to our planning committee. And what I would like to do now is talk about another sponsor for a second. So the reception that's about to follow is sponsored by ASRC Federal. So with that, I would like to play a quick message about them if I can.